Alright, welcome back. This is a problem from section 1.3. It's problem 96. It's on page 118. It says a ball is thrown vertically upward from the top of a building 96 feet tall with an initial velocity of 80 feet per second. The distance s in feet of the ball from the ground after t seconds is 96 plus 80t minus 16t squared. The questions are, after how many seconds does the ball strike the ground? After how many seconds will the ball pass the top of the building on its way down? Alright, so we're going to do this algebraically, and we're going to use the calculator graphing utility to also answer this question. Alright, so let's write this down. We'll draw a picture. This is problem 97. The equation is S equals 96. 96 because the person is throwing the ball from starting 96 feet in the air, right? So that's, I believe S is the distance. In feet, the ball is above the ground. So it starts out 96 feet above the ground. Plus 80t, that's because the person throws the ball straight up at 80 feet per second. And that's why it's positive, so it's going to go up, but it'll start coming down. Minus 16t squared. The minus 16, that's the speed of gravity, or the acceleration due to gravity. So the ball is going to fall at 16 feet per second every second. So every second it gains another 16 feet per second in speed as it falls. So let's start off with the question, after how many seconds does the ball strike the ground? So I'm going to do this first with the graphing utility, and then we'll look at how to do it by hand. So let's go to our graphing calculator, and I suggest you go ahead and do this with me. Put it in your calculator. 96 plus 80x minus 16x squared. Alright, now let's think about the window settings. Alright, so I don't want to see just any part of this graph. There's certain parts of the graph I'm interested in. If I hit graph right now, I'm probably not going to see it. I see a little bit right there. It looks like I see where it actually hits the ground. If I hit zoom 6, which is a standard setting window, you can see I see some of it, right? I don't see the top. So in this problem, t represents, I think, the number of seconds, right, after ball is thrown. So negative numbers don't make any sense here. So these negative values have no practical meaning. So when I go into my window, I'm just going to go ahead and start it at 0. You can start before that if you want. You can start at like -1, just because you might want to see a little bit to the left of what you're interested in. The max, well, I'm really not interested in looking at what happens to the function after the ball hits the ground, right? And remember, x is the time, so this ball's going to fly maybe 5 seconds. So I'll put in 5. I'll just take a look and see if that's about right. And maybe 5 isn't great enough, so let's put in 7, see if that works. Alright, yeah, so it looks like 6 is when it comes back down and hits the ground, right? So now I'm interested in, well, how far up do I need to see? The ball starts up at 96 feet above the ground, so y max needs to be bigger than that. And remember, he throws the ball straight up. So if I put in 96, that's going to show me some, but it's not going to show me the tip of this parabola. And remember, this right over here, this part is pretty much meaningless. This is like just part of the function that doesn't really have a practical application. Alright, so I'm going to guess. How high do you think this ball is going to go? I'm going to put 150 feet. See what that gives me. That was not high enough, right? So let's go in and put in 200 feet. That does it. So it looks like the ball maxes out at about 200 feet. Now remember, this is not a picture of the flight of the ball, right? The ball actually was thrown straight up, so it goes straight up and then it comes straight down. This is a function that describes the height of the ball per second after the ball is thrown. So if I hit trace here, you can see that my cursor in the top of my calculator is kind of being interfered with by that function. So I need to go up a little higher than 200. So I'm going to go into my window, change that to, how about 225? Alright, now I'll hit trace. Alright, so now I can see my cursor without it being overlapping with my function right here. And it looks like the ball goes about, what, 196 feet, maybe? 196 feet is as high as it goes. To figure out, I don't know if that was a question, let's see. After how many seconds does the ball, it isn't a question, but I'm going to answer it anyway. So if I want to know how high the ball goes, I want to know the vertex of this parabola. So I can go to second trace, maximum, enter for left bound, then you go over to the right side of the hill, the vertex I should say, enter, enter. And I can see at 2.5 seconds the ball reaches its peak of 196 feet, right? So that may be a question on a quiz, right, where I ask you, where does the ball how high does the ball go after it's thrown? So you'd be looking for the vertex of the parabola. Alright, to figure out when it hits the ground, I want to know that point right there, and it looks like 6 exactly. If I go to my table, I can scroll down and see if 6 is it. And it is, because I have a 0 there, right? So 6 is when the height is 0 feet above the ground, therefore at 6 seconds it hit the ground. So the question is answered, t equals 6 seconds is to hit the ground. Alright, so that's part A, just by using my calculator. The second question was, how many seconds will the ball pass the top of after how many seconds will the ball pass the top of the building on its way back down? So we can see that right here. It started at 96 feet, right? So when it hits 96 feet again, that's when it passes the building. So let's see if we can, I don't know if you can see my screen very well, but there's 96, beautiful. So at 5 seconds, it passes the building, right? And then it takes one more second before it hits the ground. So that last second, it fell 96 feet. So we would say after t equals 5 seconds, the ball fell to 96 feet, which is the height of the building. Alright, so how would I solve this by hand? Well, the first one, I'm interested in when does it hit the ground. Well, it hits the ground when the s is 0. Remember, s is the height above the ground. So I would just replace s with 0. So it would be 0 equals 96 plus 80t minus 16t squared. And then I need to solve this equation. Now, if you're solving it by hand, you might want to reduce these if you can. And all these are even, so I know I can at least cut them in half. And you can do that by dividing everything by 2 because it's equal to 0 over here. So I could do, what is 96 divided by 2? Is even again, so I think 4 will work if I divide by 2 again. 24. So I wonder if I could divide by 16. 96 divided by 16. It does. 80 divided by 16. Alright, so basically these numbers are all divisible by 16. So I'm going to divide everything by 16 just to make the numbers smaller and therefore easier to work with, because I can. So this is 0 equals 96 divided by 16 is 6. 80 divided by 16 is 5, so that's 5t minus t squared. Alright, and I could also make that t positive because I think this thing's going to factor. As a matter of fact, I know it's going to factor because the answers are whole numbers. And since the answers are whole numbers, it's going to factor. So I'm going to multiply everything in here by -1, every term, just because I want that t squared to be positive, right? And then I'm going to turn it over here. So when I change that, it's going to be t squared. That's going to be minus 5t. That's going to be minus 6 equals 0. Alright, so now this should factor. Two numbers that multiplied at -6 but add up to -5. What would that be? Well, I guess -6 and 1, right? -6 and 1 should work. So when I multiply -6 to 1, I get -6, but when I add -6 to 1, I get -5. So now t equals, you set both of these equal to 0, right? So t plus 1 equals 0, and t minus 6 equals 0. Because as long as one of these are 0, it's going to multiply to 0, right? 0 times something is 0. So you need to check both. And this gives us t equal -1, which can't be a solution. -1 seconds does not make sense, so I ignore that one. T equals 6 seconds does work, so that's the answer for that. Alright, what about the other one where it passes the building? Well, if it passes the building that's at the top of the building, then it's at 96 feet, so I just make S 96. So it'd be 96 equals 96 plus 80t minus 16t squared. Alright, so the 96 here will just cancel, and then I can factor a t out. So I'm going to do that. I'm going to take away 96 from both sides. And that gives me 0 equals 80t minus 16t squared. Now, since both these have a t, I can factor the t out. So z equals t times 80 minus 16t. Alright, so it's factored. Set each factor equal to 0. So t equals 0. Remember, at t equals 0, it is at 96 feet, right? Because that's how tall the building is. So but that's not the one we're interested in. We want to know when is it at the height of the building on its way back down. So that's going to come from this. This is 80 minus 16t equals 0. So negative 16t equals negative 80. And if I divide negative 16 into negative 80, I believe I get 5. So that's the answer I'm interested in. Alright, so that was problem 97. I also want to do one. I want to do one more of those open box problems. Alright, because I'm pretty sure that's going to be on at least a quiz or a test. So let me look at that again. Suppose you have a piece of sheet metal. And let's just make it 3 by 5, right? So this is 3 inches, and this is 5 inches. And I'm interested in creating a box, an open top box out of this, and I want to maximize the volume of the box. I want it to hold as much as possible. So just like before, if you watch the previous problem, I'm going to cut the corners out as a square. Now I'm making them 1 right here, but that doesn't mean that's going to be the answer, right? I don't know. Remember, if you cut too big of a square, it's not going to hold any. At some point, it's not going to hold anything. It's just going to be else. If you think about it, if I cut the square so big that there's nothing left right here, then it's just going to fold together. The two sides are just going to fold up like you're folding a sheet of paper in half, right? There's that pretty spot where the volume of the box is going to be maximized, right? So the bottom of the box is going to look like this, right here. And then these are going to fold up. Right? These are going to be gone, and you're just going to fold it up. So let's call this X, because the question is, how big of a cut do you need to make, right, in order to maximize the volume? Alright, so when I'm done, the box looks like this. That's the side of the box, let's say, and it goes back here. Alright, so there's the box. And the cut right here is going to be the height of the box. So the height of the box is X. Well, what's this part of the box? Well, this was 5, wasn't it? Right, from here to here is 5. But you cut out a square size X, leaving this. So it was 5 minus both of these cuts, right? So that's 5 minus 2x. That is the size of the cut. And this one over here is the same. It was 3, but you took out x here and x here away from it. So you're left with 3 minus 2x. So these are the dimensions of the box in terms of x. And if you want to find the volume of the box, well, you just multiply them all. So the volume of the box is equal to x times 5 minus 2x times 3 minus 2x. Now this is not quadratic. This is actually cubic because you have x, x, x. But the reason I'm bringing it up is because we're not going to solve this by hand. We're just going to look at it on the calculator and see what we can get from it. So if I plug this into my calculator, x times 5 minus 2x times 3 minus 2x graph. Alright, so you see I have this function. It's a, here's the, in case you didn't see that part, there's the function that I plugged in, and there's the graph that I have so far. Just like the last problem, I'm not really interested in this whole graph, right? Only so much of it makes sense to me because it's a practical problem. So x, remember, represents the size of the cut that you make in the box. So then what's the smallest x I'm interested in? Well, obviously, I can't make a cut smaller than 0, so I'll put in 0. And what's the biggest my cut can be? What's the maximum size cut? So what's the maximum x can be? Well, this is the shortest side of the box. So if you were to cut right here and make a cut this big, the biggest it could possibly be would be, what, 1.5? Because this would be, if this is 3, then half of that's 1.5, and that's 1.5. So if I go to 1.5, maybe a little bit more to 2, that's going to cover it for me, right? And then I'll leave that at 1, or since it's only go from 0 to 2, I think I'll put it at 0.05. So every tick mark will be at ½ an inch. Alright, y represents the volume. of the box, right? So the volume, the minimum the volume can be is 0. But again, I might want to see a little bit below that, so I'll put in -5 just so I can see a little bit below the graph. What's the maximum the volume can be? Well, that's the question. We don't really know, so we'd be guessing. It's a pretty small piece of sheet metal, so I'm gonna guess, and just by looking at the previous picture of the graph, I'm gonna guess it's pretty small, so I'll start out with 10. That would be 10 cubic inches. Let's see what happens here. Alright, so you can see that I'm really just interested from here to here. And in my window, oh, I put 0.05. No wonder there's so many of those. I'm going to put 0.5. Alright. And we can see that right here at about what, 0.5, 1.5, the volume is back down to 0, right? So right there, up at the top, is where the volume is maximized. So it looks like it's somewhere around cut size 0.63? No. I'm looking at this number. I want to max that out, right? About 0.6 inches. To find it, I just go to second trace maximum, enter, go to the right, enter, enter. And it looks like 0.6, if I round to 2 decimal places, 0.61 is the max. So, and the max volume is actually 4.1 cubic inches. Alright, so X should be about 0.61 inches to maximize the volume. The max volume is about 4.1 inches cubed. Alright, so hopefully from this you can see that you can use your calculator by thinking about these word problems, the practical restrictions on the domain, right? So in this problem, the domain is the domain is what x values make sense here. So the domain was what x values range from 0 to what did we say, 1.5, right? That's, you only need to set your window up to see from here to here on the x values. And then your y values, those have restrictions as well. That's your range. And a lot of that, some of it's guesswork, some of it isn't. For instance, I knew the volume couldn't go below 0, so there's a lower restriction on the volume, or y. And that's it. So thanks for watching.